So our next question is 2115 LeetCode medium level problem. Find all possible recipes from the given supplies. So you have information about n different recipes. You're given a string array recipes and a 2D string array ingredients. The ith recipe has the name recipes of I, and you can create it if you have all the needed ingredients from ingredients of I. A recipe can also be an ingredient for other recipes. For example, that is ingredients of I may contain a string that is in recipes. Examples we'll discuss later. You're also given a string array supplies containing all the ingredients that you initially have, and you have an infinite supply of all of them. We need to return a list of all the recipes that we want to create, and you may return the answer in any order. Note that two recipes may contain each other in their ingredients. Okay, so let us see the example. So recipes is bread, ingredients we have yeast and flour, supplies yeast, flour, and corn. So we can create bread since we have the ingredients yeast and flour, right? So we can create this recipe. This is at the 0th index, so we need these to form it, and since we already have the supplies, we can make it. Now recipes, second example is recipes is bread and sandwich. At the 0th index, we have recipes of 0, that is bread, and ingredients required to make it are yeast and flour. For making a sandwich at the index 1, we have recipes of 1, that is sandwich. So at index 1 of ingredients, we require, in order to make the sandwich, we need bread and meat, and the supplies that we have are yeast, flour, and meat. So you see that we can create bread since we have the ingredients yeast and flour in our supplies, right? Yeast and flour are in supplies, and the ingredients required to make bread are yeast and flour itself, so we can make the bread. But now we can create sandwich as well because we already have meat in our supplies. But since we were able to make bread in the recipes from our ingredients, we can also add that to supplies, right? Because now bread can be made. So since bread can be made and meat is also required, which is already in existing in meat, we can make a sandwich as well, right? So since we have the ingredient meat, we can create the ingredient bread. Similarly, we have another example. So bread, sandwich, and burger. So the first two remain the same. Now, in order to make the burger, we need what else? We need sandwich and meat and bread. So you saw that sandwich and bread we can make from the supplies, right? Since yeast and flour are required to make bread. Okay, let me show you like this. Yeast and flour are required to make bread, which is given in our ingredients and in the recipes respectively on the 0th index. So we have been able to make bread. So bread would be added to supplies. So now since we have bread and meat are available in our supplies as well now, and ingredients required to make our sandwich is bread and meat. So basically we can make sandwich as well. So we add into our supplies, we can add sandwich as well. And now the ingredients required to make our burger are sandwich, meat, and bread. So since sandwich and bread have been added to our supplies and meat we already have, we can make the burger as well. So this is the explanation. And now let us get to our solution. So basically we will be using toposort. So the insight is that this is a dependency resolution problem. So a recipe can be cooked only when all of its ingredients are available, either from supplies or previously cooked recipes. The problem is analogous to topological sorting in a directed graph, where nodes are recipes, edges are ingredient to recipes, right? Where recipe is the dependency, and a recipe with in degree equal to 0, that means no unmet ingredient requirements, can be made immediately, right? So we don't have any requirements, so we have in degree equal to 0 for that recipe. So we can make it immediately. Our approach is simple. We use a BFS based topological sorting, that is Khan's algorithm. So supplies as initial available nodes. So any recipe whose all ingredients are already in the supplies can be made, since we don't need any additional ingredients. So all the ingredients are already in supplies. That recipe can already be made. So we have in degree equal to 0, and we push it into our queue, because these are the starting. These are the points that we'll start from, right? Graph construction is something like this. So for each recipe, recipes of I, if the ingredient is not in supplies, then we mark a dependency from ingredient to recipe at index I, and increase in degree of I, that is number of unmet ingredients. Okay. Next, we start our BFS, that is push all recipes with in degree I equal to 0 into a queue. Then we process the queue. So we pop a recipe, add it to the result list, treat that popped recipe as a new supply. So we add it to the supplies. For all recipes dependent on this new recipe, we reduce their in degree. If any recipes in degree becomes 0, we push it into the queue. The standard topological sort, and result, all recipes added to result are the ones that we can make. Now time and space complexity of this basically is O of V plus C, because we are using Khan's algorithm. So V is the number of recipes. So since it is a BFS, O of V plus C it will take, and E is the total number of ingredients, that is ingredient to recipe dependencies. And space complexity again O of V plus C for adjacency list, in degree array, and Q. Now let us get to the important part, that is code. So Khan's algorithm of V plus C, right? Find all recipes is our main function. So it takes the vector string type recipes, vector string of ingredients, and vector string supplies, right? So the three things we need: recipes, ingredients, and supplies. N is recipes.size, we set it. Then we convert the supplies to a set for O of 1 lookup. So in the set we add all our supplies, begin supplies to end supplies we have added to the unordered set, and we maintain a map to store the dependencies ingredient to recipe, right? So this is of type string. String is because we are taking the ingredient here, and vector of int is basically the recipe. Okay, so it would be storing the indices, so vector of int. Now in degree of I is the number of missing ingredients, so we declare this vector of int in degree. And for basically we're going over all the recipes. For int I is equal to 0, I less than I plus plus. For each string ingredient in ingredients, and check each ingredient in this basically. So if in the set we are not able to find the ingredient, if ingredient is not present in supply set, that is if not sd.count ing. So if you are not able to find it, this recipe is dependent on the ingredient, and the ingredient is not already in supplies. So we need to create a dependency and add it to our map. That is our adjacency list. So adjacency of ing dot push back the index, right? So we are storing the recipe index, and in degree of I plus plus. Now our BFS toposort. So initialize the queue with all recipes that have in degree equal to 0. So queue we form, and for going over all the recipes, if the in degree of that recipe is 0, we push it into the queue. We start from this these particular recipes, and result in this we'll store our final answer. So while the queue is not empty, we extract our node, that is our recipe, from the top, from the front of the queue, and pop that element out. So recipe is recipes of node, and push that recipe inside our final answer. That means the recipe can be made because all the recipes with in degree 0, that means they do not have any dependency on other ingredients that are not already in supplies. So they can always be added. So that is why we have added the recipe in our final answer. And now treat this recipe as a new supply. So for all recipes depending on it, reduce their in degree. This would be treated as a new supply because since this recipe can be made, then the recipe that was actually dependent on an ingredient which was not already in supplies can be added to our supplies, right? So we go over all the neighboring indices in the recipes adjacent, basically the node recipe, and we have formed the graph. So we go over all the remaining nodes or the connected nodes, and we reduce the in degree of the neighboring index, and we check if the in degree of the neighboring index becomes 0, then we push it into the queue, and finally we return the result because these are all the ones that we can make, right? So that is about this video.